Can everyone hear me? All right. So just background on myself for 2 seconds. I'll be a freshman undergraduate at Cornell University this fall. I've been working at Stony Brook University doing research for the past 2 years. And the research that I'm going to talk to you about today is simulating surface materials, preparation for the exploration of airless bodies. And this is basically the just a synthesis project, trying to, and let me go to the next slide. What we're trying to do is synthesize minerals as similar as we can make them to what is found on a variety of airless bodies, primarily the moon, in relation to the RISE node, which this is a part of. There we are. So this is has relation to the RISE's first research theme and third research theme, primarily, in that we're trying to create synthetic minerals to be used as standards to enable quantitative remote geochemical analysis of airless bodies, with the idea that the same minerals that we create with very well-controlled chemical composition and characteristics, those same minerals can then be used for toxicology studies to understand what's the likelihood of damage to lung tissue for astronauts if they inhale this kind of material that is very similar to what we find in lunar regolith. So we have in this project, which is going to be going for the next 5 years, we actually have quite a variety of things which we're going to be trying to synthesize. This isn't even an exhaustive list, but so far we've started on synthesizing plagioclase, similar to what would be found in the Northsites of the lunar highlands, as well as pigeonites that can be similar to what can be found in lunar basalts. And then later on we'll be making a variety of complex rocks to study a number of other effects. But so the reason why we're trying to create standards for plagioclase, obviously we have standards for taking, for example, mid-infrared emissivity spectra or visual near-infrared reflectance spectra of plagioclase. But in the Northsites of the lunar highlands, what's interesting is that even though plagioclase is a solid solution between anorthite and albite, between calcium aluminum silicate and sodium aluminum silicate, in some of the low-sodium plagioclase crystals, the iron or magnesium content can actually rival your sodium content. You can get up to 1 weight percent FeO, and if you have 2 weight percent albite, the idea is that small changes in FeO versus MgO content of plagioclase crystals could possibly be used to help identify different kinds of lithologies on other planetary bodies. And so what we set out to do is form or synthesize large crystals of plagioclase, upwards of 100 microns in small dimension, which would have a variety of different iron and magnesium contents, maybe 1 weight percent FeO, 1 weight percent MgO, and then an intermediary. And then also a spectrum of different anorthite versus albite ratios. And in these samples, we actually, since we can control the oxygen fugacity, we sought to create plagioclase crystals which would include metallic iron spherules, which is seen in lunar samples. And notably in these samples, we want to synthesize them such that there will be no other crystalline phases other than plagioclase, because if, for example, we formed olivine in our samples, it would be very difficult to separate those. So what we did is we made an oxide mix of a particular composition which we picked out, which is listed here at the top. It shouldn't make much sense at the moment. It's about 64 weight percent anorthite, 3 weight percent albite, 9% forsterite, 13% phalite, and 10% excess silica. And while, again, that won't make much sense, if you break this down to mole percent, what we tried to do is have a 95:5 anorthite albite mole ratio, so that when we fully melt this mix and synthesize plagioclase from it, we'll get an overall plagioclase composition of around AN98, which is what we're looking at in comparison to the phononothrosites. We also wanted a one-to-one ratio of force-red to phthalate to add a magnesium and iron component. And what's important to note is that we are trying to, we're synthesizing plagioclase in a melt that had magnesium silicate and iron silicate components, as opposed to simply taking a melt of plagioclase composition and adding FeO and MgO. Because if you try just adding MgO and FeO to a melt of plagioclase composition, you actually get a wide field of spinel stability. And so what ends up happening is that you can't synthesize much plagioclase before you start getting secondary crystalline phases, which is undesirable. Then decided that we should have a 3-to-1 plagioclase to olivine weight ratio, so that we can synthesize a large amount of plagioclase per sample, but that we would still have a notable iron and magnesium content of our melts. And then we added 10% excess silica to our melts, which has two purposes. It further lowers the melting temperature of our mix, and also helps to destabilize crystalline spinel, so that we hopefully won't get those secondary crystalline phases. And so then at the bottom we have just kind of the overall composition rewritten in a somewhat more understandable way. So our actual synthesis experiments were carried out in metallic iron capsules, an image of which is in the upper right-hand corner. These were in sealed silica glass tubes under vacuum and under a small pressure of nitrogen. So these were at low oxygen fugacity, and the melt was saturated with metallic iron. And what we did is we fully melted the sample to destroy all plagioclase nuclei, and then performed dynamic cooling so that we would manage to minimize plagioclase nucleation and maximize growth, so as to create large crystals of plagioclase. Then, of course, since if we didn't quench, we would end up getting olivine or spinel, we quenched these samples into liquid gallium, and we have not yet gotten to the last step of this, but plan to separate our plagioclase crystals from our melt using cell-frag equipment, which I can't really say much about because we haven't started using it. So these are some of the first results of our synthesis experiments. This is in our petrographic light microscope. On the left is a reflected light image. On the right is a polarized light image with cross polarizers. And what you can see, sort of on this projection, is that we managed to make crystals of around 200 microns in small dimension and up to 1 millimeter in large dimension. And so that's definitely the size that we need to get accurate emissivity and reflectance spectra of these samples. And this is just to zoom in on one of those plagioclase crystals. If you can see the whitish spots in this crystal, this is reflected light, those are metallic iron spherules. So we did manage to create a large amount of metallic iron spherules included within these crystals. The largest one, which you can see around over here, is around 17 microns. We actually have no lower bound on the size of these spherules, because if you just keep zooming in our visible light microscope, you see them as small as maybe half a micron, but we just can't see any smaller than that. So in order to use these as standards, we'd like to know their composition, and we typically use an electron microprobe for that. The only problem with doing that for this kind of a sample, to get, for example, the iron content, is that if you look at, for example, we have a 5-micron beam size. And as I said earlier, we have no lower bound on the size of these metallic iron spherules. So we can't really pick one 5-micron diameter on our sample, which we can definitively say includes no metallic iron spherules, which then, if we took an analysis there, that analysis wouldn't be representative of the true dissolved iron content of the plagioclase crystal itself. In addition, there would be no meaningful way to correct for secondary iron fluorescence when you're analyzing a phase which has very little iron that is directly adjacent to a phase that has, near 100% mole percent iron. So what we sought to do to properly analyze the iron content of these plagioclase crystals is actually to make new plagioclase crystals. We had previously done experiments in involving just a phthalite plus plagioclase composition melt, where we decided if we replace some percentage of the ferrous iron of our mix with ferric iron, Fe2 plus with Fe3 plus, and then do the same experiment, we actually found that you can end up with a melt that has no remaining ferric iron, but has a noticeably reduced amount of metallic iron spherules in it. And so what we did is we took the same bulk composition of mix and made another sample so that the overall mix will have, and the melt will have the same iron content, the same mole percentage of iron ions, but that would feasibly have fewer metallic iron spherules. This is a electron backscatter image of these resulting plagioclase crystals, which we synthesized. And while it's difficult to see in this image, because unfortunately we didn't manage to get our samples back in time for the conference, the only metallic iron spherule inclusions you can see are little white dots spread throughout these crystals. And you may have to take my word for it. We did manage to make samples that have many fewer metallic iron spherules, but still have a roughly the same overall iron content of the melt and of the as compared to our sample, which is made with no excess ferric iron. And so that's the current state of our work on synthesizing plagioclase standards. We're next moving on to, at the moment, unfortunately you can't see this graph very well, but we're moving on to the synthesis of pigeonites. And pigeonite standards are an interesting topic because we don't really have many of them. And I don't have a phase diagram up here, unfortunately. Pigeonite is stable at high temperatures if it contains around 10 mole percent calcium silicate. But the problem is that while you can synthesize plagioclase at high temperatures and it's found in quickly cooled lunar basalts, as you cool your pigeonites, they invert into orthopyroxene or orthopyroxene plus augite. And so what happens is that if you do find pigeonite in a rock, it's typically a quickly cooled rock and therefore will have very small crystals of pigeonite. And if it's a slowly cooled rock, you won't find any pigeonite at all. So there are no real natural samples of pigeonite which can be used for standards. And so what we sought out to do is synthesize pigeonite in such a way that you would have no orthopyroxene. One second. In such a way that you'd have no orthopyroxene, no augite, but that you'd have large crystals of pigeonite up to, again, 100 microns in smallest dimension, and with a range of iron-magnesium contents from around 10 mole percent iron to around 80 mole percent iron as compared to iron plus magnesium. And that would be done, if you see this polythermal diagram, in the iron-rich compositions, we can form them at low temperatures, roughly 900 degrees, and we should be able to form them hydrothermally, whereas at the more magnesium-rich compositions, we should be able to form them in a silica glass tube in a vacuum. All right. So that's all. Any questions? Sure.
Okay, it's working. Yes. We have one question back there, Carly. Yes.
These experiments are fascinating. I'm looking forward to seeing the results. But I have a question, and I just probably didn't hear it right. When you were describing some of the goals of your mixtures, your mineral glass mixtures, specifically for the plagioclases, you said you were going to have 1% iron in the plagioclase, or was that for the metallic spherules?
No, so the and thank you for pointing that out. No, the idea was to have ferrous iron does partition into plagioclase, not just as metallic iron inclusions. That would be roughly 1 weight percent of ferrous or any ferric iron in the plagioclase.
Well, but I'm coming from looking at lunar plagioclases, et cetera, and the most ferrous-rich plagioclase is not more than even 0.5% iron. So I don't understand why you're going to 1%.
No, sorry about that. No, and we don't get 1 weight percent of ferrous iron in these samples. That was kind of a benchmark which we were aiming for. The idea is that if we can identify iron content of plagioclase, we can make a wide variety of iron contents of plagioclase.
Okay. Well, the one I encourage you to, for the lunar and some of the asteroid applications, to do it between the 0.1% to maybe 0.5%. That's sort of the range.
That's actually the iron contents we're getting.
Okay,
right
wonderful.
around there, around 0.3% actually.
Oh, great. Okay, well, I look forward to it.
All right.
Any more questions? Yes, one more.
My name is John Chapman. On Earth now in the mining industry, just in the last 5 years, people have started looking for aurorite, which is a metallic globules like you see here in the plagioclase, and it's made up of 75% nickel, 25% iron. And the grade of that is 0.15 to 0.2% nickel in the rock. And some of the big mining companies now are doing feasibility studies on actually mining those and separating the aurorite alloy using just magnetics. It's quite a change, game changer, and it's well worth watching.
That's very interesting.
Okay. One more. Did you mention how much sample you're making?
So for the variety of, we're trying to make our current benchmark for plagioclase, we're making around 0.25 grams. But thankfully, the idea behind it is once we establish a procedure for making these large crystals of plagioclase, which we have, we can really make, while our batches make somewhere between 0.1 grams and 0.5 grams typically, we can do that as many times as is necessary to create more material to use as standards.
All right, thank you. Thank you very much.